Good evening, all of you. So let us start a new chapter today. I think we completed acids and bases. Today we'll discuss thermodynamics. Okay, so from this you'll get one question. Okay, so this is completely numerical part. Now in thermodynamics, this is the terminology we are going to use. System. System means the portion which is under observation. The portion which is under observation. That is what we call system. Next, surroundings. Next is surroundings, right? So let us see what are surroundings. The portion other than system in the universe. Okay, so that is what we call surroundings. That means system plus surroundings. What you will get? That gives you entire universe. The next part will be types of system. Types of system. How many types of systems are there in the first one? Open system. So what is open system? In open system, both energy as well as matter exchange takes place from system to surroundings and surroundings to system. So that is what we call open system. Then next, closed system. Now what is closed system? So in closed system only matter exchange takes place. So only matter will exchange from, only energy. Only energy exchange takes place. So only energy exchange takes place from system to surroundings and surroundings to system. That is what we call closed system. Next one, last one, isolated system. Isolated system. Now what is isolated system? Neither energy nor matter exchange takes place. Exchange takes place between system and surroundings or system to surroundings, right? So neither energy nor matter exchange takes place. So this is about types of system. Then extensive properties. So what are extensive properties? Let us suppose any property, you take any property which depend on total quantity of the system, which depend on total quantity of the system. So that is what we call extensive property. Like how? Let us suppose if you want to measure mass, volume, okay, energy, So you want to measure mass of a substance. You have to consider total system. Then only you will find out total mass of that system. So they are called extensive properties. Next, intensive properties. Next is intensive properties. What are intensive properties? Any property which do not depend on total quantity of the system. Total quantity of the system. So that is what we call intensive property. Like example, if you take density, boiling point, melting point. Okay, so all these properties are intensive properties. There is one point that ratio or product or sum of any two extensive properties is intensive. What does that mean? You take ratio, product, or sum of any two extensive properties, that becomes intensive. What is that? Example, take ratio of mass and volume. So mass and volume both are extensive properties. But if you take its ratio, then it will become density. It will become density. So mass by volume is equal to density. Density is intensive property. What is density, sir? Intensive property. So this is all about extensive and intensive properties. Next, thermodynamic processes. What is it, sir? Thermodynamic processes, right? So in that first one, isothermal process. What is isothermal process? dt is equal to 0 or du is equal to 0. That means temperature remains constant. There is no temperature change. There is no change in internal energy. What is U? U is nothing but internal energy. So in the isothermal process, change in temperature as well as change in internal energy becomes 0. Then adiabatic process. What is adiabatic process? Q is equal to 0. That means there is no heat absorbed in this system. There is no heat absorbed in this system. Next, isobaric process. Isobaric means constant pressure. That means there is no change in pressure. There is no change in pressure. So that is what we call isobaric process. Next, isochoric process. Isochoric process. What is it? Change in volume is 0. Change in volume. So that is delta V is equal to 0. Then delta H is equal to 0 and delta U is also 0. Next one, cyclic process. So in cyclic process, what will happen? So this is delta V is equal to 0 here. So here we'll consider in cyclic process, Initial and final states are same. Initial and final states are same. That means delta U, change in enthalpy will be 0. Delta H will also be equal to 0. So this is cyclic process. Then work done. Work in irreversible process. In irreversible process, W is equal to minus P external delta V. Then we'll see different cases here. We'll see different cases here. Work done in reversible isothermal process. Work done in reversible isothermal process. What is that? So W is equal to minus 2.303 nRT log V2 by V1. Next, work done in reversible adiabatic process. So the formula for that W is equal to 2.303 nRT log V1 by V2. So here this is equal to minus 2.303 nRT log in terms of pressure P1 by P2. Here in terms of pressure log P2 by P1. Okay. Next, heat capacity at constant volume. Heat capacity at constant volume, that is given as CV. That is given as CV. So W is equal to NCV into delta T. Work done is equal to NCV into delta T. Then heat capacity at constant pressure. Heat capacity at constant pressure, that is CP. Second, W is equal to N into CP delta T. Okay. So next, relation between CP and CV. So very familiar, CP minus CV is equal to R, or CP by CV is equal to gamma. CP by CV is equal to gamma. Next part will be first law of thermodynamics. According to first law of thermodynamics, delta E is equal to Q plus W. Okay. Then enthalpy. So this is represented by H. So expression for delta H. Delta H is equal to delta E plus P delta V. P delta V means work done. So delta E or delta U plus work done. But we know that P delta V, PV is equal to nRT. PV is equal to nRT. So you can take in place of P delta V, you can take delta nRT. So therefore, delta H is equal to delta E plus delta nRT. Understood? So this is relationship between delta H and delta E. So here delta E or delta U, both are same. Delta E and delta U, both are same. So please mute your audio. Next, entropy. What is entropy? It is a measure of disorderness. If you consider entropy of gas, entropy of liquid, entropy of solid. So entropy is denoted by S. What is it? A measure of disorderness. In which case you'll find more disorderness in gas. So entropy of gas is greater than entropy of liquid than entropy of solid. So this is about entropy. And change in entropy is given by amount of Q absorbed by T. Q by T. Q is amount of heat absorbed. Q is amount of heat absorbed. So this is regarding entropy. Next. We'll move to second law of thermodynamics. So all spontaneous processes are thermodynamically irreversible. All spontaneous processes are thermodynamically irreversible. Or other statement, heat cannot flow from colder body to hotter body on its own. Colder body to hotter body on its own. So the second law of thermodynamics. Next, Gibbs free energy. So this is denoted by G. What is Gibbs free energy? G. That is the amount of energy available to do useful work. So what is it? Energy available to do useful work. That is what we call Gibbs free energy. That is what we call Gibbs free energy. So for a spontaneous process, delta G is always negative. Delta G is given by delta H minus E delta S. So this is expression for delta G. If delta G is equal to 0, what does that mean? The system is in equilibrium. The system is in equilibrium. If delta G is equal to positive, then the process is non-spontaneous, because delta G should be negative for spontaneous process. For spontaneous process. Then last statement here is third law of thermodynamics. Third law of thermodynamics. So what is third law of thermodynamics? The pure and perfectly crystalline substance, a pure and perfectly crystalline substance, entropy is zero at absolute zero. What does that mean? You take any crystalline substance. In the crystalline substance, entropy is zero. What does that mean? Disorderness is zero. That means it is perfectly arranged. But that will happen at absolute zero. Absolute zero means 0 Kelvin or minus 273 degrees Celsius. Okay, so this is what we call limit. Absolute temperature should be 0, then entropy becomes 0. So limit S, limit T tends to 0, S becomes 0. So this is about third law of thermodynamics. Last topic, Hess law. What is Hess law? The amount of heat change, is same whether the reaction takes place in single step or several steps. Single step or several steps. What does that mean? Let us suppose the reaction is going on. A gives D. So this is single step. Here delta H is equal to, let us suppose, minus Q. Same reaction, A gives B, B gives C, finally C gives D. A gives B, let us suppose delta H1 minus Q1, B gives C, delta H2 minus Q2, C gives D, delta H3 is equal to minus Q3. So therefore, according to Hess law, the amount of heat change in single step should be equal to the amount of heat change in several steps. So delta H is equal to minus Q, minus Q1, minus Q2, minus Q3. You make it common minus, then finally what is get? Q is equal to Q1 plus Q2 plus Q3. So this is your final step. Done. So this is what we call Hess law. This is what we call Hess law, right? So now let us move to numerical part. So theory part we finished. Okay. So let us move to numerical part now. Because from this chapter we'll get only numericals, no theory question. Mostly expected question will be numerical part only. Right. So let us see some numerical questions, then Yes. Shall we start? Calculate the work done. So question number 1. So you're moving to numerical part now. In that first question, calculate the work done. When 1 mole of water, 1 mole of water at 373 Kelvin, at 373 Kelvin vaporizes against an atmospheric pressure and pressure of 1 atm. Assume ideal gas behavior. Assume ideal gas behavior. Okay. So this is given now. So what is work done minus P delta V. So P is external pressure. Then what is change in volume? What is change in volume? So calculate work done of 1 mole of water at 373 Kelvin vaporizes against atmospheric pressure. So if you consider 1 mole of water, so the volume occupied by water is very small, and thus the volume change in is equal to the volume occupied by 1 gram mole of water vapor, 1 gram mole of water vapor, right? So in that way, let us consider what is its volume. So volume occupied by water is very small. So change in volume is considered as volume occupied by water vapor. Do you know what is volume occupied by water vapor? No. So then how will consider volume occupied by water vapor? So this is found by volume. We know that PV is equal to nRT, isn't it? Then what is volume, sir? nRT by P. So what is number of moles given? 1 mole. So 1 into, what is R value? 0.0821. Temperature, 373 Kelvin. Pressure, 1 atmospheric pressure. What is pressure given? 1 atm. So substitute all these values and you'll get answer in later atmospheric pressure. Okay. And substitute those values and let me know what is that value. 1 into 0.081 into 373. What you will get, sir? .0821 into 373. Can anybody tell me what will be that answer? What you are getting? 30.6 around. So, isn't it? You are
Yes, sir.
getting 30.62. So, later atmospheres. Later atmosphere. So, always convert into joules. So, how we can convert into joules? 1 liter atmosphere. So, this conversion, you remember, 1 liter atmosphere is equal to 101 joules. Actually, this is 101.3 joules. So 30.6 into 101.3 joule. So that will be your answer. So what is that? 101.3. So 30.62 into 101.3. That will be your answer. So you will get around 3101. Isn't it?
Yes, sir.
3000. This will be your solve that question. Okay. A gas expands 0.5 liter against the constant pressure. What is the pressure? Pressure of 1 atmospheric pressure. Calculate the work done in joule. Work done in joule. And one more point I'm adding here, calorie. So to find out that work done in joule as well as calories also. But here a gas expands by 0.5 liters. So that means change in volume is given here. Pressure is given 1 atm. Work done. What is work done? Minus P delta V. So what is pressure given there? 1 atm, 1 into change in volumes 0.5 liters. That means minus 0.5 liter atmospheric pressure. Now to convert into joules, minus 0.5 into 101.3 joules. 101.3 joules. So what you will get? 0.5. That means 1 by 2. 1 by 2 means what you are getting? 50.664 joules. 1 liter atmospheric is equal to 24.20 calories. So to convert liter atmosphere into calories, multiply with 24.20. So then what you will get, sir? Again, 0.5 consider as 1 by 2. So it is 12.10 calories. This is minus, this is also minus. So this is work done in both joules as well as calories. Joules as well as calories. Then last model in this work done. Question number 3. So I'm moving to question number 3 now. Okay. calculate, next question. Calculate the work done. Calculate the work done in open vessel. In open vessel at 300 Kelvin. 300 Kelvin. When 92 grams of sodium reacts with water. And here assume ideal gas nature. Now, this is the question, sir. So what we are doing, calculate work done in open vessel at 300 Kelvin when 92 grams of sodium reacts with water. Actually, what happens if sodium reacts with water? So Na plus H2O gives rise to 2NaOH plus H2. This is gas, hydrogen. And here, what is the amount of sodium used? Number of moles of sodium is equal to 92 by 23. It means weight by molecular weight. So here atomic weight is 23 for sodium. So 92 by 23, how many times it will go? 4 times. Okay. So here you can see, so number of moles of sodium is 4. I'll write that equation once again. 2Na plus 2H2O gives rise to 2NaOH plus S2. Now here it is clearly visible that 2 moles of sodium produces 1 mole of hydrogen. 2 moles of sodium gives 1 mole of H2 from the equation. But now here how many moles of sodium are obtained? Here you can see 4 moles. So 2 moles, 1 mole means 4 moles of sodium gives how many moles? 2 moles of H2. So what is volume of H2 here? So number of moles of H2, 2 moles. Okay. Now our question is calculate work done. So write work done formula. W is equal to minus P delta V. That means minus P, volume occupied by hydrogen, minus P into volume of H2, which is equal to number of moles of H2 into RT. Okay, so that is equal to number of moles of H2, 2 moles here, minus 2 into R value. So this we need to find out in joules. What is R value in joules? 8.314 into 300. So finally what you're getting minus 4988 joules. This is work done when 92 grams of sodium reacts with water. One more question. Okay, proceed with one more question. Following or not? Okay, write down question. Question. 2.8 grams of nitrogen gas at 300 Kelvin and 20 atmospheric pressure was allowed to expand isothermally against a constant external pressure, of 1 atmospheric pressure. Then calculate delta U, Q, and W for the gas. Okay. Now 2.8 grams of nitrogen gas is there at 300 kelvins and 200 atm. It is allowed to expand isothermally against a constant external pressure of 1 atmospheric pressure. Then what is actually volume of N2? Is it given? No. So we need to find out first volume of N2, right? But at 20 atmospheric pressure, it means initial volume of N2. What is it? Initial volume of N2. Because work done formula, what is work done formula? Minus P external pressure into delta V. What is delta V? V final minus V initial. That means final volume is minus initial volume. But we don't know what is final volume and what is initial volume. But based on the given conditions, now nitrogen gas is present initially at 20 atmospheric pressure and 300 Kelvin. So using those values, let us find out initial volume first. Initial volume of N2. What is formula? PV is equal to nRT, or V is equal to N by P into RT. What is the number of moles of nitrogen given there? 2.8 grams. Weight is given. So number of moles means weight by gram molecular weight. That is 2.8 by 28 into R value. So R value later atmospheric 0.0821 into RT, universal gas constant. What is R? Sorry, this is pressure, right? This is pressure. What is pressure, sir? Initially, nitrogen gas is present at 20 atmospheric pressure. Okay, then RT, R value 0.0821. Temperature is given, that is 300 Kelvin. 2.8 in 28, 10 times. So this 0 gets cancelled. 0 gets cancelled. 3 by 2. So that is 1.5 into 0.0821. So let's multiply 0.0821 into 3 by 2. 3 by 2. That gives the initial value. So what is that value? Initial volume. What you got there? If you multiply that and divide with 2, then you are getting 0.123 liters. So this is first, we calculated initial volume. Final volume. That is V2. Okay. So finally, what is pressure, sir? Again same. P is equal to nRT or V final is equal to nRT by T. Number of moles of nitrogen. Same weight by gram molecular weight. 2.8 by 28 into R value. 0.0821. Temperature. Same temperature. But now, what is this pressure? Pressure finally, what is the pressure? 1 atmospheric pressure. 1 atmospheric, 2.18, 10 times 0, 0. So 0.0821 into 30. What you'll get, sir? 2.463. So now we have initial volume as well as final volume. Now this is substituting W is equal to minus P delta V. So what is external pressure, sir? Minus 1 into delta V. Final volume 2.463 minus initial volume 0.123. So this is how you are getting the later atmospheric pressure. Now, if you subtract and multiply with minus 1, you get minus 2.340 later atmospheric. So this is work done. This is work done. So you convert later atmosphere into joules. So you multiply with 101.3 joules. So finally, what you're getting minus 236.95 joule. Okay, just 1 minute. So we'll move to, so this is work done. So what we need to find out actually, so we'll move to next problem then. Okay. So that is in joules. So work done in joules we obtained there, right? Now, next part in this problem, I think still we need to find out what else we need to find out. Very Q and delta U also we need to find out. What is Q and delta Q? So what is formula said? Q is equal to delta U plus W. So what type of process it is given, sir? Where is it? Isothermal. Which process? Isothermal process. Already we discussed that for isothermal process, delta U is equal to 0. For delta U is equal to 0, right? So then what is Q, sir? We need to find out last term. Q is equal to W. Q is equal to W. So what is W? Already we have W. What is that? Minus 236.95 joules. So this is Q value. So we found what is work done. Then delta U for isothermal process is 0. Then Q is equal to minus 236.95 joules, right? So this is all about calculation of work done and amount of heat absorbed Q. Right. So we'll proceed with one more problem. We'll proceed with one more numerical, that is, a system is provided, another question. A system is provided 50 joules of heat and work done on the system is, work done on the system is 20 joules. What is the change in the, what is the change in the internal energy? In the internal energy. So system is provided 50 joules of heat. That means amount of heat absorbed by the system is 50 joules. That means amount of heat absorbed Q is equal to 50 joules, right? And work done on the system is work done on the system. So W is equal to work done on the system is positive, that is plus 20 joules. Then the question is about what is change in internal energy. Delta U is equal to Q plus W. So what is Q? What is Q, sir? 50 joules. W is equal to 20 joules. So what is that? 70 joules. What is it? 70 joules. Next, the same model, similar model. The only change is, one more question. The work done by a system. The work done by a system is 10 joules. Is 10 joules. when 40 joules heat is supplied to it, when 40 joules heat is supplied to it. Calculate the increase in the internal energy of the system. The internal energy of system. So what is it? The work done by a system is 10 joules. When 40 joules heat is supplied to it, calculate the increase in the internal energy of the system. That means delta U, sir. Calculate increase in internal energy means what is change in delta U? What is change in delta U? So let us see. Now here, so please notice this difference here. Work done on the system. Work done on the system, we are considering plus. Now here, work done by the system, not on the system. Work is done by the system. Okay, then work done by the system. So that is minus, what is that? Minus 10 joules. Minus 10 joules. Then amount of heat. What is the amount of heat supplied? 40 joules. What is the amount of heat supplied? 40 joules. Then, as usual, change in delta U is equal to Q plus W. What is Q, sir? 40. W is minus 10. So that is 30 joules. So this difference you should understand. This difference you should understand. What is that? Work done by a system and work done on the system. Work done on the system, that is positive. Positive for work done on the system. Then here, work done by the system. Work done by the system will be negative. Work done by the system is negative. Did you understand? So this is what we call work done by a system and work done on the system. Work done by on the system and work done by the system, right? So this is about problems based on work done. Problems based on work done. We'll move to next model now. We'll move to another model once again. We'll check some other models also. So next very frequently asking model is based on enthalpies. Okay. So what type of questions you will get based on enthalpies? Okay, we'll see this model also, then we can wind up this session. Calculate, move to next model. Calculate the enthalpy of formation of ammonia from the following bond energies. From the following bond energies. So this is given data here. NH bond energy, enthalpy of NH bond is equal to 389 kilojoules per mole. Next, HH bond. This is all given data. HH bond is 435 kilojoules per mole. Next, N triple bond, N bond. So that bond energy is 945.36 kilojoules per mole. Right? Now, enthalpy of formation of ammonia. How you will get ammonia acid? We know that N2 plus 3H2 gives rise to 2NH3, isn't it? So how you will get ammonia? N2 plus. N2 means N triple bond N plus 3 HH gives rise to 2 N H here, H here, H here. 3 NH bonds. 3 NH bonds, right? So here, one NN bond is broken, 3 HH bonds are broken, and 2 into 3 NH bonds. That means total 6 NH bonds. So this is 1 NH bond, 2 NH bonds, 3 NH bonds. Total 6 NH bonds are formed. Now let us calculate how you can calculate enthalpy of formation of ammonia. Enthalpy of formation of ammonia. So let us check it. Delta H formation. That is given by delta H of N triple bond N plus delta, how many HH bonds are? 3. Delta HH bonds. Okay, so this is reactants. Number of bonds dissociated minus number of bonds formed. Number of bonds formed. How many bonds formed? 6 NH bonds. That means delta H of NH bonds. So delta H formation. Here I am giving you delta H of formation. That means change in enthalpy of formation is given by number of bonds dissociated minus number of bonds formed. Number of bonds formed, right? So how many bonds dissociated here? This bond is dissociated, 3 HH bonds are dissociated, and 6 NH bonds are formed. So now keep all those values. Delta H, NN bond. What is NN bond, sir? 945.36 plus 3 delta HH bonds. 3 moles of HH bonds. Where are HH bonds? 435. Okay. Minus 6 NH bonds. What is bond enthalpy NH bond? 389. How many? 389. So just multiply and add those values. Finally, you find out what is that value you are getting, say. So after that, finally, you'll get minus 83.64 kilojoules. That calculation you do it later. So this is that value you get. So this is for total 6 NH bonds, but calculate enthalpy of formation of ammonia. That means only 1 mole of ammonia. But here, how many moles we calculated? 2 moles. So 2 moles this much, then for 1 mole. That means final step. Heat of formation of ammonia. That means 1 molecule. So that is minus 83.64 by divided by 2. What is that? Minus 41.82 kilojoules per mole. Minus 41.82 kilojoules per mole. So this is about heat of formation of ammonia. Heat of formation of ammonia, right? So this is how you'll get problems based on heat of formation. Heat of formation. Next, one more question similar to this. How much heat will be required? So I'm moving to next question. How much heat will be required to make 2 kg calcium carbide. Calcium carbide, that is CaC2, according to the following reaction. According to the following reaction. Then, so what is this? CaO solid plus 3 carbons solid gives rise to CaC2 solid plus CO gas, carbon monoxide gas. The heats of formations of formation of CaO, CaC2 and CO, carbon monoxide, are minus 151, minus 14, minus 26 kilocalories. Okay. Now you need to find out how much heat will be required to make 2 kg of calcium carbide. Okay. Now let us find out actual heat required for the formation of 1 mole of calcium carbide. Okay, so this is 1 mole, isn't it? Here, you can see this is 1 mole. So find out what is the amount of heat required for formation of 1 mole of calcium carbide, right? So then delta H formation is equal to change in enthalpy of products minus change in enthalpy of reactants, right? So how many products are there? CaC2 and CO. What is CaC2? 14. So minus 14. Then CO minus 26 minus reactants. Reactants are calcium oxide and 3 carbons. So what is calcium oxide heat? Minus 151. Minus 151. Plus how many carbons? 3 carbons. So formation of carbon, it is in elemental form. Elemental form means there is no heat of enthalpy required. 0. That is 0. So what you will get, sir? Minus 14 minus 26. Minus 40, minus of minus, plus 151. Then what you are getting? 111 kilocalories. So this is amount of heat required for formation of 1 mole of calcium carbide. So 1 mole of calcium carbide requires 111 kilocalories. What is 1 mole? Molar mass of calcium carbide. What is molar mass? 40. Here I will take. What is molar mass? Calcium 40. 2 carbons, 2 into 12, 24 grams. Requires 111 kilocalories. That means 64 grams requires 111 kilocalories. But for how many grams we need? 2 kg. 2 kg means 2000 grams. 2000 grams requires. That means 111 by 64 multiplied by 2000. So this is 2000. So what you will get here. 111 by 64 into 2000. So what does that mean, sir? 3468.75 kilocalories. So this is what you will get. 3468.75 kilocalories of heat required for the formation of 2 kg of calcium carbide. 2 kg of calcium carbide, right? So this is how you should solve questions from thermodynamics, right? Only 2 models are there, sir. Only 2 models are there. One is, this is based on types of enthalpies and Hess law. And first model is based on work done. So this is about thermodynamics. Try to practice some other questions also. Then you will get a clear idea about numericals based on thermodynamics, right? So tomorrow, we completed chemical equilibrium also. So I think, yeah, some basic concepts in chemistry. So one more physical chemistry chapter is left behind. So there is some basic concepts in chemistry and redox reactions. So that we'll see tomorrow, so that we can finish first PU complete physical chemistry. Then we are left with maybe organic and inorganic chemistry, because already we completed atomic structure as well as periodic classification and chemical bonding also. So only if we can complete some basic concepts in chemistry, then we'll move to hydrogen, S block and P block elements, and we'll move to, what is that? Hydrocarbons, right? So that's it for this session. Meet you tomorrow once again. Good night, all of you.